So this is my master's thesis I am going to present here today, titled Segmentation of Pavement Cracks in North Cyprus using deep learning. So I'll be going through the presentation according to this table of contents. I'll go right into the presentation. The introduction and problem context. The core problem is that cracks, of course, they are common across the roads and they vary in size and visibility. And so if untreated, these cracks worsen over time, leading to serious damage like potholes. The rapid deterioration then underscores the need for more effective road management strategies. The goal of the study is to develop a CNN-based system that can segment pavement cracks to improve road maintenance and safety. Challenges of manual detection. So before the introduction of CNN, these tasks was being done in a more traditional way, like for instance, manual inspection, which is definitely slow and subjective. For instance, someone goes in there to inspect the road. If two people go in there, they may come up with a different conclusion or different reports. So that's a challenge there. And then you have highly computational limitations. These were such as thresholding edge detection, which were often noisy and highly sensitive to illumination dynamics, which means different lighting, not generalizable, and therefore these methods require extensive manual feature engineering to isolate the cracks. The more recent and promising solution, which is deep learning. The deep learning offers a promising way to analyze extensive data which can detect cracks more precisely and effectively than human teams and other methods like the thresholding. Normally, this can be done in real time or even can help also in predictive maintenance. So specifically, the CNN architecture selected for this problem was UNet. UNet is a U-shaped architecture. We'll discuss it more in one slide ahead. It was developed to automate the extraction of features from the images. For instance, when you have an image, there will be portions in the image that will be cracks, and then there will be portions that are actually not cracks. So the algorithm is able to learn in the image which part of the image is cracks. So this algorithm can do that autonomously by learning the features of the cracks, which may be represented, of course, everything in an image is represented in pixels. So it learns the pixels that represent cracks and then the pixels that represent non-cracked areas. So visually, this is how the UNet architecture is represented. It's usage, as I said earlier. So in the network, in the neural network, you have various inputs. You have the filters, and then the images. In my example here, in the image, and actually in my implementation, I tried various parameters, which I'll discuss in the upcoming slides. So you have the size of the image and the number, the filter numbers, which are the inputs to the neural network. So for instance, here you see 120 to 128 by 3, which means these are RGB images, 3 channel. And then starting with 16 by 16 filters. So the filters are responsible for learning the features in the images, the pixels that represent cracks. So as you go from block, so this is one block in the network, this is another. So each block in the network has its own filters. Of course, the same image in an instance is propagated through different blocks of the network. So here, actually, you can specify actually the size you want. It can be mostly 128 by 128 or 256 by 256. And then it decreases downwards through the contraction path, which is this one, up to the base, and then after the base going upward, the expansive path, you start increasing the number, the image size again. And the most important part actually in this network, neural network, is what is known as a skip connection. It helps the network to maintain the features that it learns in the contraction part while it's on the expansive part. So what that does helps the network, the neural network, to maintain the critical spatial information that it has learned here. For instance, the filters, when multiplied by the pixel numbers, it helps to know which location on the image that feature has been learned from. For instance, if the crack is on the top left of the picture, when this filter is being multiplied with the pixels on that location, because of these skip connections, when it gets here, it's able to remember that information. Basically, that's actually what makes the units very unique and powerful from every other CNN architecture. That was a brief overview of the main algorithm chosen for this task. And there are other operations that happens. Convolution is happening here, and this is max pooling. So convolution is where the filters are slided over the images to learn the features. And max pooling is basically there to reduce unnecessary information in order to make the algorithm really efficient for solving the problems. And another operation here is another operations that can be added. For instance, a padding, same, which means keep the image size in the same block of the same size. Here there are two operations, convolutional operations. So you are saying the image size within this block should remain the same. And then there is dropouts. It helps prevent something known as overfitting in deep learning, where the neural network learns the training data but does not perform well in the test data. Methodology, I'll just go briefly over it. So you give the image and then you process the data by generating the mask beside the image and the marks, and then split the data sets. So here you have normalization, scaling the pixel. The pixels are numbered from 0 to 255, but to make the algorithm efficient, it's scaled down to between 0 and 1 to make the value smaller, which helps the algorithm perform better. And then the data has been split, training, validation, and then testing data set. And then on the training and validation data, you do the training and validation loop. So this can happen for a number of epochs until the algorithm neural network has learned the features, or the number of epoch sets in the network has completed. Methodology continues from validation to testing. So in testing, we are testing the output here if the prediction map, every value in the prediction array that is set is being checked against this condition. So for instance, if a value, the output from here normally is a probabilistic value, which can be from 0 to 1. But because this is a classification problem, which we only need it to be either crack or no crack, or 0 or 1, that is why we need this to convert such probabilistic values to 1 or 0. So that is what this condition is doing. So if the value is like 0.4, it's normally classified here as a no crack because it's less than 0.5. But if the probabilistic value is above 0.5, then a crack. And then eventually you have the evaluation, which happens here. You have various evaluation metrics and the results. This was the methodology employed in the study. The implementation details, I've already mentioned most of them. So the strategy was to build the network from scratch. There is normally a concept known as transfer learning, where you can employ an already trained neural network. But here, we used a network. We trained the network from scratch to make sure that it learns the features in the images. I explained this already, and the activation functions are included in the network. We have ReLU and sigmoid. The sigmoid is what's responsible for giving the probabilistic values, and then the ReLU is there to introduce nonlinearity in the network. It helps actually the network to learn the features. And we have the loss function, which is there to quantify the error in the network, and the optimizer, which is there to correct sort of the network according to the response it gets from the loss function. And data splits already mentioned earlier. The experimental setup, these are the batch size, normally the number of data points that the network goes through before it completes one epoch. So we tried various batch sizes to see the performance. And then you have the image size also. We tried different sizes, the number of filters, as well as the introduction of a bottleneck dropout. We will see the effects of various parameters. The evaluation metrics here, they were discussed previously by presenters, discussed machine learning. So I wouldn't go deeper into that again. But precisely for this problem, precision and recall are very important, as they focus correctly on predicting the positive class, which is the cracks, which represent a very small percentage of an image. And the more even important metrics are, which is intersection over union. It measures the overlap, the predicted and the actual image. These are the results from the experiment with various parameters summarized in this table. Because of time, I'll just go through the key summary. So the overall model performance, the union model demonstrated promising results in segmenting cracks to achieve higher accuracy consistent with the training, validation, and testing. While the accuracy was constantly high, precision and recall showed greater variability, suggesting a challenge in balancing crack identification with minimizing false positive, which can be evidently related to the quality of the data, as many speakers have mentioned here. The quality of the model you get will highly depend on the quality of data used to train these models. So the best RA score achieved was 66.649 in experiment 8, with an image size of 256 by 256. So what we learned there is that bigger image size normally gives you better IOU score, which is the overlap. This is an example. This is a test image that the model had not seen during training. So after the model was trained and then given this image, it was able to differentiate clearly where the cracks are. For instance, you can see here what it predicted. It predicted that these are the cracks in the image, which proves the successful development of this model to perform this task. So most of these are already discussed. And conclusion, the study successfully developed a CNN-based unit model for automated pavement cards we saw before now in the visualization. The significance is that unit-based crack segmentation systems have the potential to significantly improve road maintenance and safety inspections. These systems offer automated, efficient, and accurate alternative for reducing land manual inspection and minimizing to personnel. Contribution, the work contributes to the growing body of research on AI-based road maintenance systems, particularly addressing infrastructure challenges in areas like North Cyprus. The picture is that I still am interested to apply units, this time on drone data to measure the impact of climate change on forest loss and landscapes, and effect of, for instance, flooding and soil erosion in theory. If you have any question, please go for it.
Amazing. Thank you so much, sir. A round of applause, please, for that amazing presentation.